Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento. This is a lecture in my Inductive Logic Phil 61 course on Ian Hacking's Introduction to Probability and Inductive Logic book. We're in Chapter 4. This is the second lecture on Chapter 4, and I'm introducing basic probability concepts. And we've talked about the addition rules of probability, and for this lecture, we're going to talk about the multiplication rule of probability. There's a couple of these we got to learn about how to understand compounded probability. So here's what's going on. In elementary cases, we ask about the probabilities of sequences of events rather than unordered sets of events. So like we're rolling dice, we'll talk about the first roll, the second roll, and so on. So on two flips of a coin, what's the probability of getting a head, then a tail? And I'll just represent that as HT when we talk about probabilities. Or on three rolls of a die, what's the probability of getting 2, 6, then 4? The operant concept when dealing with these kinds of questions is independence. So what's going to matter for our understanding probabilities of these multiple events is whether the subsequent events are dependent or independent. And we've introduced those notions in some previous lectures, and it'll come out now why it's important here. So from the concept of fairness that we talked about before, events are independent if the occurrence of one event does not affect the probability of the occurrence of the other. So with the gambler's fallacy, for instance, where the gambler, rolls the dice over and over again and doesn't get a 7, and the gambler thinks that as the rolls accumulate over time and they roll more and more times and not get a 7, that the dice are due to hit, or somehow that the probabilities are building up, or that there's some sort of causal connection from the past to the future. But rolls of the dice are independent. They don't have any dependent condition on the previous events, so the dice don't remember, they don't have any, there's no, nature is not pushing through trying to make the 7 happen through the dice. So the gambler in the gambler's fallacy has mistaken an independent set of events for dependent set of events. So now figuring out what those probabilities really are is going to require us correctly applying the multiplication rules of probability. So first off, for independent events, this is very simple. For two of independent events, A and B, the probability of A and B both happening is just the probability of the first one times the probability of the second one. So the probability of A times the probability of B for independent events. So this is simple. For if we're asking, think of it in this term, if we're asking whether or not A and B happened, then we multiply the probability that A happened times the probability of B to get the probability that they both happened. So for independent events A and B, probability of A and B equals the probability of A times the probability of B. Flip a coin 2 times. What's the probability of getting a head, then a tail? Well, it's the probability of getting a head, which is 0.5, times the probability of getting a tail, which is 0.5, which equals 0.25. So an HT is 2.5. The probability of getting heads is the same. It's 0.5 times 0.5 because those are independent events. There's no connection between them. What's the probability when I flip a coin 4 times of getting, say, 4 tails? You might think this is unlikely. It's no more likely than any other particular sequence of independent events. It's 0.5 times 0.5 times 0.5 times 0.5, which is 0.0625. So when we apply the multiplication rule for independent events to questions like coin tosses, which are independent, we just straight up multiply the number of cases. What about the probability of getting heads, tails, heads, tails? Again, the probability of each one of those independent events is 0.5. So the conjoint probability of all 4 of them is 0.0625. The probability of 4 heads, 4 tails, three tails, 1 head, 3 heads, 1 tail, whatever, any particular sequence, all of the 16 that we could describe that the 4 coin tosses might produce, all are going to come out to be 0.0625. No single one of those is more likely than the others, which actually defies a little bit some of the gamblers' intuitions. Okay, so other cases. What's the probability that McCormick's dog has fleas and is black? It's just the probability that he has fleas times the probability that he's black, because there's no condition or no causal connection between being black and having fleas for dogs, I don't think. That is the rate of fleas among yellow labs is just as high or as low as it is for black labs or any other color dog. What's the probability that your new roommate is a Virgo and from Dixon? It's just the probability that your roommate is a Virgo, which is 1 out of 12, and the probability that your roommate is from Dixon, which is maybe 1 out of 5 or 1 out of 20 for some random Sac State student. But there's no connection between those two, and they have there's no causal connection, so they're independent events. What's the probability that you'll get struck by lightning today and you'll get hit by a meteorite? Those are independent probabilities, so we just multiply them both, and they're very, very low. Okay, so suppose we're rolling a single die multiple times. These are independent events. What's the probability of getting a 1 and a 6? It's 1/6 times 1/6, which is 1/36. I'm just going to give you lots of examples here, and then we'll start to talk about dependent cases. What's the probability of getting a 2 and a 2? It's the same because they're independent events. What's the probability of getting a 1 or a 2 or a 5? So now we switch back to our probability rule for addition of independent events. So we add those probabilities. So now it adds up to 3/6 or 1/2. So here's a tricky one. What's the probability of getting a 1 or a 2 on the first roll and getting a 3 or a 2 on the second roll? And you should take a moment to look at the way I've written that out with the parentheses and with the or signs and the ampersand to designate which ones we're asking for. And the way we calculate this would be 1/6 plus 1/6 times 1/6 plus 1/6, which works out to be 1/9. So the odds that you get 1 or 2 in the first or 3 or 2 in the second is 1/9. Which makes sense if you think that through intuitively. And here's another more complicated one. What's the probability that you would roll a 1 and a 2 on 2 rolls, or you would roll a 2 then a 1 on 2 rolls? And notice how the signs have switched, and notice how the line here says something different than the previous line. So look at the notation and look at the English and think through the concepts and how the concepts are different. And in this case, the odds are 1 out of 18 when you run the math. And now we're using the addition rule and we're using the multiplication rule. Notice what sort of question this last one answers, and notice how they're different. Okay, so what about for dependent events? Now, a dependent event is one where the first event causally affects or changes the outcome of the second event. What's the probability that I will draw a king from this deck of cards, and then, without replacement, I'll draw another king? Okay, so these are not independent events, because if I take out a king in the first draw, so I've got a deck of cards, I pull out a king. Now, previously, there were 4 out of 52 cards in there were kings. I pull out 1 king. Now, how many kings are left? So notice I'm asking this question without replacement. So you take that king, you put it out. Now I've got a deck of cards that's 51 cards, with 3 of them are kings. So the second probability has been changed by the first event. So this is a dependent probability. In that case, it would be 4 out of 52 times 3 out of 51 is the answer to the first question. I didn't write it out in this case, but what I'm trying to get you to do is understand the notion of dependence, of how the subsequent events change in probability because of what happened in the previous event. What's the probability that Smith is a smoker and Smith will get lung cancer? Well, those are different. The probability you'll get a lung cancer changes if there's this prior fact that you're a smoker. So knowing that about Smith changes our assessment of the probability that Smith will get lung cancer. That's a dependent probability. What's the probability that my new roommate will be neurotic and difficult to live with? Well, neurotic people are difficult to live with. They're not the only sorts of people who are difficult to live with, but they do go together. So if you find out one, that increases the probability of the other. What's the probability that you roll a die and the number that comes up is prime and even? And that, again, is a dependent event. think that one through. The second probability is dependent on the first one, or the first property, if true, changes the probability of the second. Okay, so here's our rule, and here's how it's going to be written. I'm going to introduce a new logical notation, or a new concept for probability notation. It's called the multiplication rule for dependent events. So when A and B are dependent probabilities, the probability of A and B equals the probability of A times the probability of B given A. So that vertical line between the B and the A is read as, what's the probability of B given A? So for the lung cancer case, imagine, what's the probability that Smith is a smoker and Smith will get lung cancer? Well, that would be the probability that Smith is a smoker times the probability that you get lung cancer given that you're a smoker. And that's different. That's higher than the probability of you getting lung cancer if you're not a smoker, and so on. Okay, so let's look at some cases. There's our rule for dependent events. What's the probability that you will pull an ace of clubs off the top of a shuffled deck? In other words, what's the probability that it's an ace and it's a club? Well, you know this. You know there's only one of those in the deck. It's 1 out of 52. But let me show you how, when we apply this rule, it gives us the right answer. And we can use it on more complicated cases that you don't just know intuitively. What's the probability of getting an ace in the first case? Well, there's 4 aces in the deck. Once you've got an ace, and given that you've drawn an ace, what's the probability that it's a club? Note that this is a dependent probability. Well, if I pull a card off the top of the deck and it's an ace, now what's the probability that given it's an ace, that it's also a club? Well, 1 out of the 4 of the aces are clubs, so that's 1/4. So when I do the math and apply the rule for multiplication rule for dependent events, what's the probability that it's an ace and the probability it's a club? Well, it's the probability of an ace times the probability that it's a club given that it's an ace. It's 4 over 52 times 1/4, which equals 1 over 52. And that was the answer we gave. That's the answer we knew from the outset, because we know that there's only one of those in the deck. But notice we can construct that and get the right answer. This rule gives us the right answer. And now it's going to let us look at more complicated cases that you can't just do intuitively in your head. Here's a harder example. What's the probability that you'll get an ace or a black card on the first draw and a jack or a red card on the second draw with replacement? Okay, so first question, how should we write this question? Here's the way to write it. So I've written probability parentheses A or B in parentheses ampersand parentheses J or R in parentheses. The other way of writing this, and I won't read it out, but the other way of writing this gives us a different answer. It multiplies 2 different probabilities. This sentence is asking for the probability that I'm going to get that first disjunction and the second disjunction. And the numbers then, applying the multiplication rule for dependent events, is written out this way. So you can actually do the substitution now. I'll use my cursor here to point. The probability of getting an ace is 4 out of 52, and the probability of getting a black card is 26 out of 52, right there. Now, why did we remove the 2 out of 52 right here? Well, some of the aces are black, and we don't want to double count those, so we back those out right here using the addition rule for overlap cases, subtraction rule for overlap cases. Here it is written out in English. Note the use of the addition rule for non-mutually exclusive probability. Sorry, that's what I was trying to say a second ago. Since 2 aces are black, we're going to take those 2 out right there. We don't double count them. And 2 jacks are red to avoid double counting there. And we're just applying, actually this is just a straight up application of the multiplication rule for these 2 independent events. But what's important here is that we've used the addition rule for non-mutually exclusive probability. So we're now combining and using a bunch of different rules to get these sort of answers. Okay, so let's go to some simpler cases. What's the probability that when you roll 2 dice or 1 die twice that you'll get a 1 and a 1? It's 1/6 times 1/6, which is 1/36. What's the probability that when you roll 2 dice, you'll get a sum total of 7? That is, when you add the two numbers that come up, they'll come out to be 7. Well, there's several ways to get a combination of 7 with 2 dice. You can get it with a 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, and a 6 and a 1. Now, look at all of those options for a second and think about, why did I repeat 1 and 6 and 6 and 1? Well, think of it this way. Imagine I've got one die, or I've got 2 dice and I've got them. We don't usually, when you roll 2 dice, you don't think about them as being separate, but imagine we label them, call them A and B. Okay, so if I roll 2 dice, there's actually 2 ways that I can get 6 and 1 come up. A could have 1 on it and B could have 6, or A could have 6 and B could have 1 on it. And we don't usually make that distinction when we're rolling 2 dice because we don't keep track of which one's which. Or imagine they were different colors. But those are different events, and those are different ways to get 7. So those all have to be represented here, and they all capture the 6 different possible ways to get a total of 7 when you roll 2 dice. So since there's 6 different possible ways, and each one of those has a probability of 1 out of 36 of happening, then the total probability of getting a 7, that is, this is like you're playing craps and you're rolling 2 dice, the total probability of getting a 7 is 6 out of 36, or 1/6. Or the fraction, or the decimal here is 0.16. So the chart over there actually that I've got on this slide shows what I'm talking about. The highest single probability outcome for rolling 2 dice is to get a 7, and that happens a little over 16% of the time. And then in descending order on both directions, for 8s or for 5s or 2s or 12s, the probabilities go down. Well, why is that? Well, that's because there's only one way to get a 2 rolling 2 dice. That only happens when you roll a 1 and a 1. There's only one way to get a 12 when you roll 2 dice. That only happens when you get a 6 and a 6. So that can only happen one unique way out of 36 ways. But a 7 can happen 6 different ways out of 36. So it's the highest probability distribution case. So we used this in a previous example to talk about a biased system. Rolling 2 dice and summing them up has a biased output. That is to say that not all of the outputs are the same in probability. The probability of getting 7 is much higher than the others. That's a biased output. Okay, so a caveat. When we talk about sequences of events, it makes it sound like that when we say A and B, we're really saying A and then B, as if the fact that B comes after A is implied, but that need not be the case. All we really need to do is keep track of the fact that there are distinct events or distinct trials. And that's partly what I mean in my example when I said, imagine we keep our 2 dice 2 different colors, or we label them A and B. No, that'll be confusing. Imagine I've got a red 6-sided die and a green 6-sided die. So now I can roll them simultaneously, and I can talk about and capture all these different probabilities. Or I could just take one die and roll it twice, once, then again, and I've got 2 distinct events. Or in the case of the simultaneous roll, I've got 2 distinct events. The red die came up with a number, and the green die came up with a number. So the time sequence is not necessary here, but we do have to have a way of keeping track of the difference of the events and the dependence or independence of the events. So if we're flipping a coin 2 times, then we have 2 trials, call them T1 and T2. There are 4 possible ways this can go down, which are represented as follows. So in trial 1 and trial 2, we might get both H's, HT, TH, or TT. Tails, tails. It isn't important that trial 2 comes after trial 1. Both coins could be flipped at the same time. What's important is just that the 2 trials be distinguished from each other. So we might be talking about simultaneous events. We might be talking about sequential events. It doesn't matter. What matters is dependence, and these are independent events in this case. Okay, so to summarize what we've talked about so far, we've talked about the inclusive and exclusive senses of OR that was in the previous lecture. We've used and talked about the addition rule for mutually exclusive probabilities in those kinds of cases. The addition rule for mutually exclusive probabilities is that what's the probability of A or B? It's the probability of A added to the probability of B. When those events are non-mutually exclusive probabilities, when there's some connection between them, or there's some overlap, or we're double counting, then we calculate that by adding the probability of A to the probability of B, but then we subtract out the double counted part. We take out the probability of A and B in those kinds of cases. And we've got a bunch of those examples in the previous lecture. We've now talked about the multiplication rule for independent probabilities. That's the probability of A times the probability of B, straight up, just an application there. And then we've seen a few examples, and I'm going to give you many more, and I'm going to make this much clearer in subsequent discussions. The multiplication rule for dependent events is written out as the probability of A and B equals the probability of A times the probability of B given A. And all I've done here is just sort of conceptually sketch that out, but we will look at some more explicit cases and make that sharper in subsequent discussions. All right, so that's my second and final lecture on Hacking's Chapter 4 for our inductive logic class. And we'll be moving on to some more complicated notions and concepts, problems of probability theory next.